Okay. Hello, guys. Hello, class. Hello, professor. This is our project. We are creating an optimal grocery list with budget. My name is Andy Vu.
I'm Sam Heckman.
I'm Tyler Sutherland.
Okay, so this is our roadmap for our presentation. Just motivation, approach, results, and discussion. Let's get into it. So, our motivation: we buy groceries every day. Everyone buys groceries every day. Groceries get expensive, and typically people will set certain budgets aside for dedicated groceries. So we wanted to create a solution that generates the grocery list to fit everyone's personal budget. And of course, that budget restraint is the biggest thing in the problem. And so this basically turns this problem into a knapsack problem. And as we all know, knapsack is a NP hard problem.
For our approach, we wanted to make our own data set or find one in the wild. And we also used three different approaches for our algorithm: brute force, dynamic programming, and a heuristic.
So we decided to create a custom data set. We attempted to try to use data sets by other retailers. However, they have many things that are miscellaneous items, such as utensils, spices, clothing, and drinks, and things like that. So we only wanted to include food items into our data set. And of course, they have a lot of redundancy with different brands and items as well. So what we did was we used Kroger.com to shop by department. And as you can see here, this is just a quick screen capture of what that looks like. As you can see, we're in the meat and seafood section, and there's a variety of items. So we just record the item name, the item food group type, the price, and the item weight. And of course, once that's done, our first approach is using a brute force approach. So it uses IDER tools and Pandas libraries. Panda is used to create the data frame from the grocery CSV file. And then simply, as all brute force does, it finds all the possible combinations within the budget constraint, and it weighs every combination and outputs the combination that had the maximum weight.
For the dynamic programming, we used a memoization technique instead of, say, for example, recursion. This one also uses pandas. Instead of using IDER tools, it uses NumPy libraries for manipulating arrays. What it does is creates a 2D table for storing subproblems, and with these subproblems, it iterates over the data set, finding items that that so long as the weight is under max, it will add these to the possible solution list, and then of course omit items if they are if they push the bag over the current limit. This generates the list of the lowest weight items, or rather the lowest weight items for that knapsack, and returns the list. We also used a heuristic. For our heuristic, we used the genetic algorithm technique. So the genetic algorithm is a bit unconventional. It uses or is inspired by natural selection, by finding the best fit possible solutions and creating offspring over generations based on those solutions. It does unfortunately have a potential for being an infinite runtime unless otherwise set, as it may never find a good enough solution, and the global max may also not be reached. Even over a number of generations, it may never find a perfect fit solution. For our genetic algorithm, we used pandas and NumPy as well, much like the dynamic programming. The initial population for our genetic pool selects random items based upon the threshold size. So this is going to be, if the threshold size is say 10% of the total maximum, then it will select 10% of the items randomly to be in the potential solutions as initialized. It will then cross over these, or rather, it will then find the best fit of this population, take the best half, and then based upon that top half, create an equal number of offspring. Those offspring will then be subject to random mutations at a low level to induce a little bit of randomness to it, and then that population will then go through the next generation phase. And this will repeat over a set number of generations, and then at that last generation, return the best fit solution.
And then finally, for our user interface, we decided to do a Tinker library. It's a Python. It's within Python. It allows us to do input fields and checkboxes and buttons in order to create a good user experience for our users. Which we'll go over later in the results section. Basically, you input your budget, any dietary exemptions, and then hit submit, and then the algorithm takes over, and then once it computes the results, it will return a list and the total amount for all the items. Heading into our results, we start off with our brute force approach, which was very lacking when we were looking into it. It was only able to process 28 items before it became unreasonable to do so. It's really good at lower quantities, like 10 to 11 items. It's running pretty quickly, but once you start getting above 20, it becomes like a minute plus, and that's not okay. It's good, not okay for us directly, because at grocery store, 10,000 items, you don't want to do that. So it's very exponential. It was very exponential in its growth. Moving to the dynamic programming results, we see that it's actually able to process all the data points that we had and do it much quicker than brute force could. Much so quicker that it was able to process the entire data set before the 11th item could be processed, and the brute force running at a growth rate of big O n times m. It very much showed that it was able to handle larger scale stuff, but unfortunately we ran into challenges when it was picking the same items no matter what. Really, it was picking the best item for the highest weight to the least amount of money. Which, when you want diversity in food and eating stuff, you probably don't want to eat the same thing every week, and you want more diversity in those results.
For the genetic algorithm, we also got good results. Just looking at it, the runtime is not as good as the dynamic programming, but its growth is much more stable. So the runtime is going to be subject, instead of to the actual knapsack problem itself, it's going to be subject to the functions for mutation, for crossover, and for fitness selection, which by that mean, because of that, it will not grow as much with the size of the knapsack. So because our data set is so small, we really can't exemplify that here. And the really good part of the genetic algorithm, however, compared to the dynamic programming, is that because of the stochastic nature of generating potential solutions, we end up with a much better or much greater amount of diversity.
And this is just kind of how our user interface looks like and works. You input a budget of what we did was $35. You can check exemptions, and then it processes it, and then we'll output a list of items with your total price at the bottom.
Okay, so for our discussion in future works, like I said earlier, we only have 189 items in our data set. It's quite small and quite limited, so this causes problems with some of the algorithms. They can't demonstrate how well they work. We do want to increase the size, but we do run into problems of why we created a custom data set in the first place. The spices and things like that, and a lot of redundancy and overlapping. So there's a lot of careful consideration and steps that we need to take further to increase this data set size.
Now, part of the problem with our with doing this sort of project is that a normal grocery store is an unbounded knapsack. There's no real limit to how much a customer can buy. If they want to buy 10 apples, they can buy 10 apples. They're not subject to just buying one of each thing. So that means that we initially did this. However, the problem is that all of our algorithms ended up picking just the highest price to weight ratio item. In this scenario, it was always watermelons. No matter what we did, it found the watermelon to be the best price to weight ratio and filled the knapsack with that because that's what it is supposed to be doing. Our solution to this was changing it from unbound to a 0-1. Now this is unrealistic for a grocery store because, as I said, a customer is not limited to just buying one of any particular good. They can buy multiple if so long as the store has multiple. Now, however, what it does do is increase the diversity of the selected list, which is good for the customer, and it also increases the difficulty of the algorithm because the algorithm has to consider every single one of the potential items in that grocery store to fill that list.
And lastly, we had the idea of our food groups in order to diversify. In order to diversify what we had in our shopping list. And when we first thought about this, we were thinking about implementing it by ratios by the maximum weight of the algorithm. So when the algorithm was computing its lists to determine which one was the best, it would be choosing the maximum weight and try to percentivize that down into servings and stuff, which was making it super complicated and very much not great to implement at all. So instead, we thought about implementing it based on the initial budget instead, and basically subdividing that up into different quantities for different food groups. When doing research, we found that you probably want 50% of your budget to go to vegetables, 25% to go to protein, and 10% to go to grain, and you want like a slice of fruit and stuff like that. So that's what we're going to be implementing that with, pretty much.
So with that being said, here's a conclusion. The grocery list generator is much more complex and difficult than we had initially thought. A lot of it lies in the design of the problem, as well as the data set and the inventory. But with that being said, our results show, as everyone knows, brute force algorithms are terrible with unacceptable performance. And our dynamic programming is our best conventional performing algorithm, and it works for reasonably sized data sets. And of course, a unconventional heuristic algorithm like genetic algorithms work for greater, larger data sets. However, we can't fully showcase that with our limited data set. But with that being said, this is our Git link here for the source code at the bottom, and these are references. Thank you so much for watching and listening.